You are listening to the Scholar Circle, scholarcircle.org. I'm Maria Armoudian. In December, a New Zealand volcano erupted unexpectedly, killing 21 people who were visiting the island. In the Philippines, last week, Taal Volcano's eruption displaced hundreds of thousands of people. In Ecuador, warnings are coming of a pending eruption. What causes volcanic eruptions? Does climate change increase their frequency? We have three experts with us. Ivan Savov is a lecturer in the School of Earth and the Environment at University of Leeds, and he's the author of Evaluating the Relationship Between Climate Change and Volcanism. Chuck Connor joins us. He's a professor in the School of Geosciences at the University of South Florida. He's co-authored Climatic Control on Icelandic Volcanic Activity During the Mid-Holocene. Jihong Cole-Dai joins us. He's a professor at South Dakota State University and the author of Evidence of Influence of Human Activities and Volcanic Eruptions on Environmental Perchlorate from a 300-year Greenland ice core. Welcome to the Scholar Circle. It's great to have you with us here. It seems like in the past few months we've been reading about a few volcanic eruptions, including New Zealand and the Philippines, some warnings in Ecuador and others. I suppose I wanted to start with trying to understand if this is just normal volcanic activity or if these eruptions seem to be increasing in frequency. Chuck Connor, would you start us?
Sure. Pleasure to be here. I would say that these recent eruptions are more or less run-of-the-mill, despite their tragic consequences. It's normal rates of activity globally for volcanism. We haven't seen any long-term changes, say, over the last few decades in rates of activity. It gets our attention, especially when a couple eruptions like Taal in the Philippines and White Island happen close together in time. That's pretty much random chance. The world's a very volcanically active place, and eruptions sometimes get our attention and sometimes they don't.
So if you were going to let us know how common volcanic eruptions are, could you give us some kind of quantification on that? How often do they happen?
Globally, there's just about a volcano erupting every day. Most volcanic activity is on the seafloor, and we're only vaguely aware of that happening. For eruptions that happen on land, there are often more than 100 eruptions, 200-300 eruptions per year. So they're pretty common. Some volcanoes are very persistently active. They are almost in a continuous state of eruption. Others are dormant for hundreds or thousands of years and then suddenly reawaken, and often they have very explosive eruptions. So activity varies quite a lot in terms of rates and style from volcano to volcano. But globally, on average, things are pretty active.
So what distinguishes whether one is going to be erupting regularly or is going to go dormant for a while and then erupting? Do we know enough about these activities to sort of really understand what causes one to erupt more frequently or to go dormant and then re-erupt? What do we know about the science of what's happening?
Yeah, it's a really good question. We know some things, and some things remain a great mystery, unfortunately. But it might be worth talking about why volcanoes erupt and why they erupt. Some erupt lavas and some erupt giant explosion clouds that go 40 kilometers into the air. And the answer is really related to how gassy they are. So as the magma, the molten rock, is generated in the earth and it rises up through the crust of the earth, bubbles begin to form and vesiculate in that, just like a bottle of champagne. Some magmas are much more bubbly than others, and those bubble-rich magmas overpressure and explode and cause giant eruptions that fling rock literally tens of kilometers into the air. Some go flat, like a bottle of champagne that's been open too long, and those volcanoes erupt lavas across the surface. Now, the trick is, your question really was, do we know in advance which one of those things is going to happen? And the answer is, well, some volcanoes persistently erupt a given chemistry. We can kind of predict exactly, if things remain steady in those volcanic systems, things will progress. Lava flows will form a Kilauea and that kind of thing. Other volcanoes have much more variable activity, especially ones that are long dormant. We often don't know exactly what will happen when a new batch of magma reaches the surface. So that's a big question. Predicting the magnitude of eruptions is a big Big question for volcano scientists. We struggle with that one.
Jihong Cole-Dai, let's bring you in on this. Now, what would you add to this? Is there some way of understanding the difference? Auckland is sitting on 52 volcanoes, all allegedly dormant. What can you tell us about this? Yeah, let's hope.
Okay. I'm really glad to hear Jack talk about this because he's obviously quite knowledgeable in that. And this is really not my area of expertise. I'm sort of a chemist, but I happen to study ice cores. But about your question about, how frequent do we see volcanic eruptions? Essentially, on average, there's one almost every day. So with regard to the question of how often do we see volcanic eruptions? And of course, for each one of them may be quite random. But having studied the ice core information regarding volcanoes, I actually have something to contribute to this. Right now, I'm working on a manuscript, the volcanic eruptions that are recorded in a very long, deep Antarctica ice core that goes back at least 11,000 years. And so our data actually show that, maybe I should preface it by saying that the volcanoes that we see recorded in ice cores are usually very large eruptions. They can impact at least large regions in perhaps the hemisphere or even the entire globe. So we see these signals of these large eruptions recorded in ice layers. And going back to about 11,000 years, our data actually show that on the average, we see about 30 to 40, again, these are very large eruptions, every 1,000 years.
And you're saying large eruptions that are really disruptive, way beyond their area.
Correct. Yeah, those would be eruptions that have at least regional impact, and most of the times they have global or at least the hemispheric impact.
But we haven't had anything like that in the modern era.
Yes, we have. The one that I recall right now is the 1991 eruption of Mount Pinatubo in the Philippines. There is a kind of a rating on the scale of these eruptions. They're sort of like the Richter scale for earthquakes. So they go from somewhere from 1 to all the way up to 7 or 8. And each number there is a magnitude change of 10. So 7 is 10 times as strong as 6. So I believe Mount Pinatubo eruption is a 6. And I don't recall the White Island eruption. I haven't really looked up recently, but I believe there will be somewhere like a 3 or 4. So in the sort of historical times, we have seen at least a few very large eruptions, and these are also recorded in the ice core archive.
I guess that should really bring us to the more current research that you guys are all doing, which is the relationship to climate, volcanoes being affected by the climate, and then also how they then affect the climate. Ivan, you and Chuck have been working on research and have published a piece related to how climate change might influence volcanoes. Can you walk us through what you have found on that?
First of all, thanks for having me. And it's collaborative work that we started quite a bit of years ago, looking at the geological record of recorded eruptions coming from mostly Northern Europe. We go to look at deposits of peat or lake sediment deposits, and we started to collect the data of, the timing and then the composition of individual small glass shards, what we call cryptotephra, which record eruptions with various ages and various sources. And we start to develop a database where we try to recognize eruptions coming from pretty much one source, which in Northern Europe, the majority of it is from Iceland. And because Iceland has active climate research, it has glaciation in the past, we developed this concept hypotheses to try to determine whether there is some sort of connection, whether there is some sort of feedback. And we encountered some progress, but it's an addition to what people usually do is just numerical models, whereas we try to find something solid in the geological record, and we believe this was a powerful link. So what we found out is that the climate record coming from ice cores, from Greenland, the timing of melting of the ice caps in Iceland correlates well with periods of flare-up or decrease, depending on the timing of volcanic activity as recorded in all over Northern Europe, Germany, Scandinavia, Poland, Faroe Islands, and all across the British Isles. So this particular connection works in the way that if you have very thick glaciers, they apply more pressure in the crust, and that's why it's more difficult to erupt. But when you remove the ice caps, there is less pressure, and probably magmas can degas more freely or may explode in a very large eruption. And we believe that we see this in the record. Of course, this has a few problems. One is that the further down in the record we go, we see less and less well-preserved deposits. In the case of Antarctica, as we heard, it may be 11,000 years. In the Northern Europe, pretty much the Holocene or the last 12,000 years is the cutoff. And after this, the record becomes very sketchy and very, very difficult to determine. But it's a hypothesis, it's a working hypothesis, and the way forward is multidisciplinary look at this, combining geology and a variety of climate change science, chemistry, petrology, volcanology. All of these fields equally contribute to building a testable hypothesis. And this is what we've been doing recently.
So if I were going to try to summarize kind of the general gist of what you found, is it safe to say that when the ice sheets melt, it takes some of the pressure off of the volcano that then allows for the eruptions to happen more frequently? Chuck, did I get that right?
Yeah, you got that exactly right. That's awesome.
That's right. When we are talking about the links between climate and volcanoes, it's not only whether you have big eruptions or not, it's actually how often they occur. And there are some studies, recent publications looking at, for example, the end of the Paleozoic era or going back millions and millions of years, which found out that actually in order to make impact, you need to have pretty long periods of millions of years where you have a big eruption every few years. So that's, again, work in progress, but this recurrence rate, how often things happen, can only be determined from things that Professor Connor is studying, these recurrence rates of volcanism.
So, Chuck Connor, you just got prompted, so why don't you bring it back in?
This is an awesome discussion. So when we started this work, I was a complete skeptic. I thought there's no way we're going to find a correlation between rates of volcanism and climate change. The reason is magmas form deep inside the Earth. How is it possible that what's happening in this thin veneer at the surface is going to impact rates of melting or melt migration deep inside the Earth? And the answer is, well, it's in the data. We see this period of warming with concomitant increase in activity, and we see periods of increased glaciation in Iceland, followed by near pauses in volcanic activity. Now, every volcano doesn't stop erupting, but on average, things increase and decrease depending on this ice load. And that's just an awesome result, and it shows that the Earth's surface is coupled to the interior in ways that, are just super surprising.
Would you say then that this would be most noticeable in those fields, those volcanic fields that are currently under the ice? In other words, if you're in the South Pacific where it's not under ice, this is perhaps not going to be triggered by this ice effect, the ice melt.
Yeah, if you're in Auckland, that's not going to happen because your volcanoes are not ice covered. And so melting is not going to affect that. So But in the Arctic and Antarctic, where there are plenty of volcanoes, it likely is in effect, and that definitely will create impacts on parts of the world. So, I mean, it's a local phenomena, but, a tremendous number of volcanoes are glaciated. So, all of the high South American Andes, almost all of those volcanoes have summit glaciers. Volcanoes in Antarctica, like Mount Erebus, not so far from New Zealand, have plenty of volcanic activity and glaciers. So you even think there's some volcanoes that are currently buried under features like Ice Stream B in Antarctica. So it's not a trivial impact just because it's only happening at high latitude. It may have a profound impact on things in general. And of course, we haven't talked about the opposite yet, which is how climate is impacted by volcanoes. But that also has an impact, and that's also variable by latitude. So the interaction between climate and volcanoes turns out to be super complicated because of the complex dynamics of both those systems. But nevertheless, it's important. Nevertheless, we have to figure it out if we're going to understand how rates of activity, volcanic activity, are changing due to climate change and vice versa. It's quite a tough problem.
But Jihong Cole-Dai actually studies that reverse that you were talking about. Jihong, what would you say about that?
Our understanding and knowledge about the impact on climate by large explosive volcanic eruptions is quite good. So we know that when a volcano erupts, things come out of the vent, and essentially many of these things end up in the atmosphere. One of the important chemical species is sulfur from volcanoes. This is common from most volcanoes. Some have more and some are less, but usually you get a lot of sulfur from volcanic eruptions. And the sulfur, through its own chemistry in the atmosphere, ends up as a tiny sort of a water droplets that we call aerosols. And these aerosols happen to be the right size to scatter and reflect sunlight. So it's kind of having a cloud after an eruption. And then when large eruptions happen, these volcanic clouds or aerosols hang around for anywhere between a few weeks all the way to a couple of years. While they're in the atmosphere, they act as a kind of a shield reflecting some of the sunlight. So we know usually or typically after a major eruption, the atmospheric temperature of the Earth, or at least some big part of it, has a dip. And then that's actually verified very well with the very good measurements performed right after Pinatubo eruption. And then in our climate records and volcanic records, we can actually make a very strong link that almost every time when the big volcano erupts, we see a temperature response to that. So, and we understand the physics and the chemistry and all that quite well. But I have to just say, okay, well, this is real world science, and there may be a noise in the data, and sometimes the response may be not as much as you expected. But in general, we know, and I also have to say the response may depend on where you are on Earth. So if you're in the interior of a big continent, like where I am in South Dakota, we might experience a little bit of warming after a big volcanic eruption just because of the dynamics of the atmosphere. But by and large, we experience a cooling effect, usually on the order of somewhere between a fraction to about a 1 degree Celsius after big eruption. So, and that could last 1 to 2 years.
If you have all of these volcanoes all over the Earth, and you have more frequent eruptions because of the ice melt, say in Iceland or around Antarctica, is there a type of pressure relief? Chuck Connor, what do you say about that?
Well, not really. So we have a global system of tectonics, and so we understand well how magmas are created in the mantle of the Earth and upwell. Certainly on a global scale, things are coupled, but just because the frequency of eruptions increases in some parts of the world, like Iceland, doesn't mean that activity is going to increase globally. We don't see those kinds of trends in our data.
What about in the region of, say, does the volcano of White Island have a regional relief effect to other volcanoes in Falkland, per se?
That's a good question. So at one level, volcanoes and earthquakes, you mentioned earthquakes earlier, they are related to the stresses that exist in the crust of the earth. So there is evidence from some eruptions that they may have been triggered by an earthquake, or that the eruption itself triggered a tectonic earthquake on a regional fault that may not have occurred otherwise. And that does give us a clue that there are subtle relationships between the likelihood of an eruption, likelihood of an earthquake, and the stresses that exist in the crust. But I would add very quickly that that's kind of a secondary effect. The rates of these things sort of happen independently of those interactions. So you're not likely to see that coupling being significant on a global scale. For example, after the Tohoku earthquake in 2011, it was so devastating, and the tsunami in Tohoku, Japan, people were quite concerned that there might be large eruptions from volcanoes in the Japanese volcanic arc, but that didn't actually happen. The reason is these things aren't necessarily as closely coupled as we might imagine. So I don't think we can rely on that kind of pattern of activity. I would follow up, though, that we have not yet experienced the largest style of volcanic eruption as a technological society. Pinatubo definitely was a large eruption, a VEI 6. But remember that a VEI, a volcano of magnitude 7, is 10 times more powerful than Pinatubo, and 8 would be 100 times more powerful. So we haven't seen that kind of continental scale effect of a volcanic eruption, at least as an industrial society or a global society. Certainly humans experienced that 70,000 years ago during the eruption of Toba and other huge eruptions that happened in the geologic past. But we haven't experienced that. And so there is some uncertainty about those impacts on climate, what it'll do for us in terms of cooling and crop loss, and not to mention impact on technology. So,
do we have the technological understanding to be able to predict ahead of time a volcano of that magnitude?
Fortunately, it seems to be easier to predict or forecast very large eruptions than very small eruptions, because all of that magma moving upward in the crust actually creates a lot of disturbance. There's a lot of rumbling. There's a lot of deformation of the Earth's surface. We can observe that deformation from satellites or using seismometers on the ground. So we've actually had the most success at forecasting eruptions that are the largest because they have the best signal. Now, we might not get a lot of warning. It may only be months or weeks of warning. So that's not a lot of time to prepare for a major disaster. But we're fortunate that small eruptions are actually hard to forecast because their signals are subtle. Large eruptions, at least in our experience so far, produce pretty big signals that we can actually sense with a variety of instruments. That helps.
I wonder if also, while we're here talking about the behavior of these volcanoes and the effects of them, and particularly on climate, if we could also do an overall volcano 101. How many volcanoes do we have on the planet, and how are they spaced out, and where are most of them, and how many are alive and how many are dormant?
Well, they're very unevenly distributed across the planet. About 80% of them are around the Ring of Fire, so pretty much the borders of the Pacific Ocean. And they occur when we have development of volcanic arcs. The majority of the cases, this is where volcanism occurs. Places like Japan, Indonesia, the Philippines, where one plate goes under the other and pretty much melts. We have this intra-plate volcanism, like Hawaii, like places like Armenia, where within a plate we have weird conditions that are not common from one place to another, not as much as all the rest of the volcanism across. And probably that makes them more difficult to monitor and to predict. But in general, these volcanic arcs are the loci of volcanism. And because of this distribution, they are quite possible to link to the global tectonics, how the plates on Earth are moving. So this is very much a link between volcanoes and tectonics, or the structure of the outer crust on the Earth. So if we imagine that the Earth is made of little plates, the way they move is being well monitored and well modeled. We are making efforts to go back in the past and look how plates were rearranged in the past. And currently, we have pretty good ideas even with the speed that they move against each other. But again, it's a complex puzzle, because if you move one plate, what's the effect on all the rest of them? And is this impacting volcanoes? I think Chuck Connor touched on this a little bit, but I would probably speculate that it's quite unpredictable at this stage, both the earthquakes and volcanic eruptions. But volcanology in general is an area that we have made tremendous success and tremendous outcomes of volcanic predictions. It's a success story, whereas when it comes to earthquakes, it's much more difficult. So all of these volcanoes and climate, if I want to sum this up in a sense that there is a feedback, and one of the major things we haven't really talked is the effect of erosion, because any place we develop volcanic arcs, they don't tend to stay open for very long periods of time. In a matter of 10, 15, 20 million years, which is a very short period of time in a geological record, volcanism will stop. And then all of these volcanic rocks will erode, and erosion has a major impact on trapping and affecting the CO2. And the other big thing that is also very important as a feedback to volcanoes and where they are distributed is, again, pumping all these volcanic gases into the stratosphere. And if we're talking about volcanoes that Chuck Connor touched upon, some of these VEA7 or 8, or what's so known super eruption, we may be looking at material erupted in the troposphere, for which the impact of volcanic gases and aerosols is virtually unknown. And this is one aspect, so volcanic gases and erosion. And then another thing which we actually have seen, which is also maybe important, is the volcanic ash itself entering the sea is working as a fertilizer. So this has been seen from the eruptions in South America, and quite recent eruptions in South America, where we see massive booms and algae and all kinds of impacts to the biology of the oceans and the marine life. And this obviously has impact on climate. So where volcanoes are located is quite important. 80% around the Pacific Ring of Fire, or the rim of the Pacific Ocean. Another maybe 20% around the world. But current knowledge tells us that when it comes to aerosols, the impact will be mostly from volcanoes located in a tropic. And that's an important insight. All these glaciations that we are talking about in Alaska, Iceland, and Antarctica. So there is decoupling. Which one is more important? Again, work in progress, but there are volcanoes everywhere. And as Chuck mentioned, the last thing that is important is that we actually have very little knowledge of these very large eruptions. So some of the eruptions in Iceland that we've been studying that reach Northern Europe have pretty much crossed the entire continent. And this is by itself evident how small little particles may travel the world, sometimes multiple times. And what the impact really can be averaged out. Is a matter of a few days, you may impact areas that you haven't really thought would suffer the influence of a volcano that is long distance. Same with shutting down airports in Australia, probably New Zealand, where eruptions in South America are actually emitting a large amount of ash. So in that sense, where volcanoes are and what's their impact, again, it's a work in progress, but probably these big volcanic eruptions are the big players. And because we haven't seen one, and because most of the geological record for these big ones is either eroded or under sea, it's in the marine record, which we don't have access to, we know very little about this.
I understand that there are also these areas where we don't even know there might be a volcano.
Yes, that's correct. When it's a very massive, very big, what we call caldera eruptions, a very big eruptions, usually in the geological record or at least in the region, we can have some knowledge that they exist. And this is this predictability of where plates are, where are the plates, the edges of a big tectonic plates, how they interact with each other, whether they're colliding or whether one goes under the other. And in both cases, we can predict that there are big volcanoes. But again, in places like Hawaii, in places like interplate, in the middle of a thick plate, sometimes volcanoes may be driven by some local tectonics. And in a marine record, again, there is plenty of underwater volcanic calderas, including places like Tonga and Kermadec, and these mostly underwater volcanoes that are in the south Western Pacific. And it looks like the more we study the ocean floor, the more of these big volcanic edifices we discover, big calderas, and they have become the big discoveries of the last few years in marine volcanology, that they are much more common than we thought.
Well, this is fascinating. I just throw out a number. There is a kind of a comprehensive database of volcanic eruptions compiled by a group in UK somewhere that essentially counted about 3,000 volcanoes. Those are kind of active in the recent geological times, so that's the last few million years. So 3,000 is kind of a good number to start with. I just add maybe something that I think would be kind of interesting to think about. So we know after a big volcanic eruption, there's just this general cooling of the atmosphere. So in the kind of a global warming world, that you might think that's not a bad thing. And so that idea actually has been gaining some momentum for a while. So why don't we do something that the volcanoes do for us, which is to cool our climate? And this idea of putting the chemicals that usually are from volcanoes, put them into the stratosphere, where it would have to be high enough in the atmosphere to spread around the world. And that could create this kind of a shield. And that's called geoengineering. And that idea has been sort of has talked about it for quite a while, at least 10 years. So that's something to think about. But one sort of important thing to go along with that is that might work, but it has sort of unintended consequences. And those have to be taken into consideration if anything, any decisions to be made about that.
Such as?
Well, one thing is the chemicals that act as a sun shield for us, essentially they are acids. And then it's similar to carbon dioxide when it enters into the ocean is also acts as acid. So we have this ocean acidification problem that comes along with global warming. So if we put a lot of acidic material, by us with our hands into the atmosphere, it'll fall down as acid, and that would exacerbate the acidification problem. And that's just one of the possible unintended consequences of doing something like that.
Chuck Connor, let's bring you back in.
One thing that Alan Roebuck mentioned a few years ago, he's a professor at Rutgers University, is he pointed out that when you look at the components of our body, the oxygen, the carbon dioxide and such, that all came out of a volcano. Those components were emitted by volcanoes. So in a way, we're built of the products of volcanoes, like a lot of things at the surface of the earth. Every time a volcano erupts, it's a giant experiment on the surface of the earth. And Jihong mentioned geoengineering. Our globe runs these experiments all the time. And every time we learn something new about the way the earth works from one of these big volcanic eruptions. So I agree with him that they offer some potential for understanding how the climate behaves in response to huge impacts. Those impacts might be natural, like from a volcano, or anthropogenic, like loading the atmosphere with carbon dioxide due to industrialization. I just want to emphasize the whole thing is a complicated system, and it's really hard to understand the response. So relying on either natural volcanic activity or geoengineering to get us out of our current climate problems I don't put a lot of faith on it. I think we have to take other action in order to really mitigate the impacts of anthropogenic sources on climate. So volcanoes do that experiment for us. They're amazing natural systems.
Well, gentlemen, thank you so much for joining us here on the Scholars Circle and for sharing your research and your wisdom with us and our audiences. We really appreciate your time and your work.
You're welcome.
Thank you.
Ivan Savov is a lecturer in the School of Earth and the Environment at University of Leeds, and he's the author of Evaluating the Relationship Between Climate Change and Volcanism. Chuck Connor is a professor in the School of Geosciences at the University of South Florida. He's co-authored Climatic Control on Icelandic Volcanic Activity During the Mid-Holocene. Jihong Cole-Dai is a professor at South Dakota State University and the author of Evidence of Influence of Human Activities and Volcanic Eruptions on Environmental Perchlorate from a 300-year Greenland ice core. And that's it for today's show. Thank you to all of our guests and to those who make this program possible. To Sud Dongre, our webmaster, contributing host Doug Becker, Ankine Arasian, Melissa Chiprin, Mike Hurst, and Tim Page. Most of all, thank you for listening. If you missed part of the show, you can check out our archives at scholarcircle.org, kpfk.org, and please like us on Facebook, follow us on Twitter at Armoudian, and we'll see you next week.